All right, Module 3, recap. Here I go. It looks like I'm just talking to myself. Um, but maybe a few people will get involved. So the first key thing is when you're interpreting skeletal structures. Um, when you see the end of any line, you want to imagine that there's a carbon. And when you see any vertex, you want to imagine that there's a carbon. There are not carbons where there's a different atom shown. So here, this is a nitrogen, not a carbon. Um, so one mistake people have made is like kind of inserting extra carbons next to the nitrogen. What we call those atoms that are not carbon, we call them heteroatoms. So if you ever hear me say the term heteroatom equals an atom that's not carbon. Most common examples would be nitrogen, oxygen. Um, in a skeletal structure, heteroatoms have to be included, and any hydrogens that are bonded to heteroatoms have to be included. The key point is hydrogens are going to be implied only when there's an implied carbon. So if I draw a carbon into a skeletal structure, I have to draw in the hydrogens that are on that carbon. All right. So H's are only implied when they're on an implied carbon. So if I wanted to draw a full Lewis structure for this, I would start by just repeating the carbon chain. Then I would put in this double bond to oxygen. One mistake some people have made is not putting in a double bond, just putting a single bond to that oxygen. I could put in the lone pairs on that oxygen. The nitrogen is bonded to a hydrogen, that's shown in the skeletal structure. And then the thing that's missing on the nitrogen would be a lone pair. And now for each carbon, I'm just going to fill out their octet with hydrogen. So carbon on the end of the chain needs 3. This carbon needs 2. This carbon here needs 1. This one on the end needs 3. This carbon with a double bond to oxygen doesn't need any hydrogens because it's already got 4 bonds showing. This carbon has 2 bonds showing, so it gets 2 hydrogens. This one gets 3 hydrogens. All right, so that's essentially the key tips for interpreting skeletal structures. When you want to draw a skeletal structure, sometimes the original structure you're looking at is going to be drawn in a straight line, but a skeletal structure can't be drawn in a straight line. Skeletal structure has to be jagged because each little vertex is going to represent a carbon. So you don't want to draw skeletal structures where everything is kind of linear. Everything is going to be going up and down, alternating up and down. So if I wanted to draw this as a skeletal structure, first I'd have to, one way to keep track of things would be to number your atoms. So I have atom 1 is this carbon, atom 2, 3, 4, 5, 6, 7, 8, 9. So if I'm going to draw this molecule, I'm probably going to have kind of a jagged chain that's going to have 9 vertices. A couple of those are heteroatoms. And then, I need to have this CH3 group, which we call a methyl group. I'll call that 10. And then this oxygen with a double bond, I'll call that 11. So the way I would start would be probably to write right, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. That is going to be my main core of the molecule. Now I notice atom 2 is an oxygen. So to make space for that oxygen, I'm going to need to erase this vertex here. One mistake that people have been making is like having a vertex and then drawing the oxygen next to the vertex. So an incorrect way to draw this would be to draw like this with a vertex and then the oxygen next to the vertex. That's no good. So we'll make that into a very sad looking, crying, I don't know, looks kind of like a seal to me for some reason, but it's a very unhappy seal. Give it some hair though. All right. So don't draw your oxygen next to the vertex. Make a little space there. Don't have the two lines meet, and then draw your oxygen in. So then 1, 2 on atom 3, I have atom 10 coming off of that. On atom 4, I have the carbon double bonded to oxygen. Atom 5 is also an oxygen, so I'm going to have to make a little space there for that oxygen. Again, I don't want there to be a vertex and then an oxygen next to the vertex. I want the two lines to meet at the oxygen. Then atom 6 and 7, there's a double bond between atom 6 and 7. And then atom 8, and then atom 9 is a nitrogen, so I'm going to write NH2. I don't want to leave off those hydrogens because they're part of, they're on a heteroatom. They can't be implied. So that is an acceptable way to draw this. Now it turns out, by convention, when we have something like the left-hand side of this molecule, this part over here, when there's a heteroatom and then there's just one carbon on the other side of it, we tend to not just leave that as a skeletal structure. We tend to not just have one line coming off the heteroatom. It is acceptable, but the problem is sometimes that can get confused with a negative charge. And so a lot of times what we'll do is we'll actually write in the CH3 group there, or we'll write Me. So another way, probably the way that I would represent this molecule, would be like this. I would write OMe here. Me stands for methyl. Which is equal to CH3. And CH3 takes a fraction of a second longer to write than Me. So I will usually use Me instead just because it's shorter. And that's just because having this one line hanging out here off of the oxygen just looks a little weird. So you won't ever see me draw structures that have the one line hanging off over here. All right. Any questions about that translation that I just did? Good. All right. Formal charges can throw people off on Lewis structures. So you might see a Lewis structure with particularly formal charges on carbon, because carbon has implied hydrogens. So formal charges are going to throw off the number of implied hydrogens. If I just saw this structure over here on the left, I would say, okay, I have a carbon in the center, and then 3 CH3s around it. But that carbon only has 3 bonds, so I need to say, oh, it would have a hydrogen bonded to it. So this would look like this, CH, and then the 3 CH3 groups coming off of it. One thing I want to point out is, notice I don't always write my CH3 groups as CH3. Sometimes I write them as H3C. Same thing will go with OH groups and NH2 groups. Um, the reason is I want to show where the bond is going. And the bond is going to the carbon, not to the hydrogens. So one thing I'd like you to avoid is don't draw things like this. This looks like the bond goes to the 8 H's. So that's why we flip them around, right? H3C. All right, so this is my structure. If I just have no charge in the middle, there's an implied hydrogen. What happens if I throw a positive formal charge on the central carbon? We need to think back. How did carbon get a positive formal charge? When does carbon have a positive formal charge? It's going to be when it has 3 bonds, no lone pairs. So in this case, there is no implied hydrogen. And then this third case, what if I have a negative formal charge? If I have a negative formal charge on carbon, that means, well, to give carbon a negative formal charge, it's going to have 3 bonds, but in this case, it's also going to have a lone pair. So again, there's no implied hydrogen. Now there's an implied lone pair on the central carbon. So those formal charges have thrown some people off in the skeletal structures. So I wanted to point that out. And then I just wanted to point out some common geometry problems that you see with skeletal structures. First one comes up a lot. Looks like this. What's the problem with that? This is an alkyne, and each of these 2 carbons in the alkyne each has 2 domains. These should be linear. So instead, the way to draw that is like this. And the way I do it is I leave a little break between the single bonds and the triple bond to show that there are 4 carbons here. You know, that this is CH3, C, triple bond C, CH3. Some people are uncomfortable with that. Some people feel like, well, how do I know that there's a carbon there in the middle? If you're uncomfortable with that, it's okay in the middle of a skeletal structure to draw in those 2 carbons. You know, and you could have whatever else coming off the different parts of the molecule, but you can still draw in those 2 carbons. So in a skeletal structure, it's okay to draw in some carbons as long as you draw in the hydrogens that are on them. And for an alkyne, there are no hydrogens on them. So some people are just more comfortable drawing their alkynes with the carbons in them so that they know the carbons are there. All right, so that's one common geometry problem. Another one happens with carbonyls a lot. What's the problem with that picture? It's bent the wrong way, right? This should be trigonal planar. Right now, it looks kind of like a boat anchor. Um, so no boat anchors. Instead, you can draw it like this, or you could draw it like this. But you want your three bonds, your three domains there to be spread out. All right, sometimes people have trouble drawing tetrahedra. So this would be a typical incorrect drawing of a tetrahedron. Because what this implies is you've got two things in the plane of the page coming to a point, and then the fourth thing is going into the page but up, and the other one is going down and coming out of the page. Tetrahedra should be drawn, when you draw the two things in the plane of the page, they come to a point. The wedge and the dash should go away from the point. So if I draw the two things in the plane of the page pointed this way, the wedge and the dash should go away from that point. No matter which way I make the point of the things in the plane of the page, wedge and the dash should go away from that. This will become more important. Wedges and dashes don't make a whole lot of difference to us at this point, but when you get to Module 8, we'll see the wedges and the dashes make a huge difference. Sometimes you have the same atoms connected in the same way, but in one case something's on the wedge and something's on the dash. If you reverse those two, sometimes you can take like a life-saving medication and turn it into a poison. Yep. Do the wedges and the dashes have to be on the same side? What do you mean on the same side? The wedge and the dash should not be across from each other like this, because even if it's spread out, you want to come draw it. No, draw what's in your head. Yeah, you don't want to ever draw this. So what this would imply is essentially that the two regular lines are directly across from each other, so they're like linear, and then the other two things, one's coming towards you, and one's going away from you, and they're across from you. So that we don't want to draw. And then the last one I want to point out is when you have an alkene, alkenes are trigonal planar. When something's planar, when something's flat, that means you can represent it on the page without using the wedges and the dashes. We only need wedges and dashes when something occupies 3 dimensions. So this should be planar, so you should just draw it without wedges and dashes because it all fits in the page. So those are all the common things I saw in Module 3. But let me know if you have questions about anything else from that module.